And the distribution rule for addition and subtraction is still applied here. Okay. It's also true if this is a negative sign. Or A plus B then cross C, the order will remain A cross C and B cross C here. And the fifth formula here, we call it triple product. Okay, so look at this. B cross C, right? We do the parentheses first and then take the dot product later. Okay. So when B cross C here, the magnitude of that will give us, what is it? Yes, the area of parallelogram here. And the result of B cross C will follow the right-hand formula rules. That is why the direction of this B cross C goes to this point, this direction. And this vector perpendicular to B and C, okay? Look at the vector A. So the vector A in the plane of containing the vector A and vector B cross C here, the angle between them would be, suppose it is theta, right? So A, okay? And the magnitude of B cross C here will be H here, right? The height of this. The area of the base times the height of this parallelepiped here will be exactly the volume of this, right? And this triple product can be computed as the determinant of order 3 of these vector. Remember, the orders will be very careful here, right? Should be careful. A, B, and C. Okay? So, from these properties, the volume of this parallel, the pipette here, is given by the absolute value of this triple product. Okay? Remember here, this, the last one here, should be an absolute value of cosine theta. Because the volume is not negative, right? But somehow, if we take it's direction sensitive. So if the cosine theta here, if the angle theta is larger than pi over 2, smaller than pi, right? In that case, cosine will be a negative number. That is why we need an absolute sign here to avoid the negative things here. And in short, the volume of this will be magnitude of this guy. So suppose we are given the 3 vectors, determine the a parallelogram, parallelepiped here. If in the special case, a vector, the volume of that is 0, this means these vectors should be at the same plane, right? Or we call it, we call it coplanar. When vector A, B, and C sit on the same plane, okay? For example, show that these vectors are coplanar. Or in other words, show that they are at the same plane, okay? So what we can do here is to simply apply the formula here, right? Let us do it. Now, let us compute A dot B cross C here. Okay. From the formula, we know that it should be determinant of 1, 4, 7, 2, -1, 4, and 0, -9, 18 here, right? Sorry? -7, thank you. Yeah. Very good. Thank you, Luke. So applying the determinant formula of order 3 here, what do we have? Suppose we consider the first element here, right? That is number 1. We multiply with this determinant of order 2. And what is it in this case? Very good. Thank you, Walid. Right, we cross the column and the row containing this element. So it leaves the second order of determinant here. I mean the order determinant of order 2. And the second one, it will be, thank you, and very good. Right. And the last one. Here it will be. Thank you, very good. So we should write it carefully, yeah. Here, then this guy would be 1 times -1 times 18, right? And what is it? Yes, or -9 times 4 minus 4 times here, it will be. Thank you, Victoria. And the last one. And 0 times -1 here, right? Okay, what do we have here? It is -18 plus is plus 18, right? 36 minus 18, it will be 18. So 1 times 18 will be 18. Okay. Here is -4 times 36. Very good. And here it will be -7 times -18, right? Or it will be plus 7 times 18. And this is 0. Very good. So 18 is the common numbers, right? If we factor 18 out, what is left here? Yes. And what is it here? Yeah, simply 0, right? We factor it so that we can deal with small numbers here and see it easier. You can use calculator and multiply 436, but it becomes big. Take you some time, right? Don't have to do that. So anyway, the triple product of these vectors is equal to 0. It means that the volume of the parallelepiped here is 0, or these vectors A, B, C are coplanar, or they're sitting at the same plane. Okay, that's it. It's very useful formula. Okay, good job. Do you have any question? So just apply the formula, right? So the last formula, okay, the last formula here, the number 6, okay, A cross B, B cross C, and then cross A. Remember, we should do the inner parentheses first, right? It will be this relation, A dot B, A dot C. What is the result of A dot C here? It's scalar, right? And times B here, it will be a vector, right? And here A dot B will also be a scalar. So this is the subtraction of 2 vectors. Makes sense, right? Because on the left-hand side, it is a vector cross a vector. So makes sense. And this formula, we call it vector triple product of ABC. That's it. And here, torque is an application in physics. Suppose that, okay, the force F is acting on the rigid body here. Like we can see in this figure. R is the radius. I mean, this is force F, R is this vector, okay? Then the torque T here will be a vector, which is R cross F, okay? Look at this. Remember that it should follow the right-hand rules as well. Okay, this is vector R, okay? Look at this. If your index finger is R, right? Your F force is the middle finger. Then your thumb will be pointing this way. That is why we have the torque like this in the picture, right? Torque T tau here. You see it? Right hand rule. Okay.
How do you do this?
So okay, you see it? This is R, right? R pointing this way, and F is pointing this way. Therefore, the torque tau should point like this. Imagine it yourself. So master your skill of observing the right-hand rule. Okay? If suppose now we have the vector F pointing this direction, right? Then tau here will be pointing in the opposite direction. Do you see it? Because now R, this is suppose R because it's pointing this way. So the vector we can look at this. Okay. See it? Yes. The index fingers is the first vector. The middle finger is the second vector. The thumb would be the result vector of this cross product. Okay. Imagine it. Then it will make a rotation, this, okay? From the theorem before, the magnitude of tau will be nothing else but the magnitude of R cross F, which is the magnitude of R times magnitude of F and sine of the angle between them, R and F, which is this angle, okay? So let us do this example. This is a range, right? The force, suppose the force here, F, is 40 Newton here, pointing this way. So the distance from this to the position where we apply force here, we call it the vector R, right? So R, let us see, if we extend it here, R will be similar to this vector, right? They have the same value. Then R cross F, and the angle between them is theta here, right? How does the torque vector look like? Suppose this is the plane, right? Then it is pointing to the wall. See it? Right? Like this. Ah, it's hard. Okay. Then it's pointing to the wall, and the magnitude of that will follow this relation, the formula. Absolute of torque here would be absolute of R, absolute of F times sine of the angle between them. So then we can find it. Remember this one is 75 degrees. Okay. Okay. Then we can find the torque, magnitude of torque vectors like this. And here, the vector torque here will be the magnitude of that times the unit vector in that direction, right? That direction in this case is the vector pointing to the wall, through the wall, right? Okay. And we can compute this vector definitely, right? Using the cross product rule. Okay. Now let us continue to the new section, section 7.7.